Okay, we are putting on our geometry hats today and diving deep into crystallography.
Hmm.
This isn't just about pretty rocks, you know? This is the fundamental science that dictates the structure of virtually every solid-state material out there,
That's right.
from the mountains under our feet to the highly complex semiconductors in your electronics.
Exactly. Our source material today gives us a really comprehensive look at the essential concepts.
Right.
Things like the geometry, the symmetry, and even the surprising history behind crystals.
And our mission here is to take these, let's be honest, sometimes dense foundational
They
concepts
can be.
and really extract the pure, actionable knowledge. We're aiming to bypass the intimidating mathematics as much as possible.
Focusing on the core ideas, the shapes, the rules.
It's an incredible journey, really. We're going to explore a scale that stretches from, well, cosmic dust all the way to objects the size of houses.
Which is amazing in itself.
Then we'll investigate the ironclad laws of symmetry that govern these structures. And then, right near the end, we'll unveil a scientific upheaval
Yeah, a real revolution.
caused by a geometry that was once considered, mathematically forbidden.
By the end of this deep dive, you should have a much clearer understanding of that deep connection between the atomic arrangement inside a material and its final macroscopic shape.
We'll learn why materials have internal directional properties. That's anisotropy.
The anisotropy, exactly. And we'll discover how every external crystal shape ever observed, literally all of them, can be classified within just 32 specific classes.
32. That sounds manageable. Okay, let's get into it. So to truly appreciate crystallography, you really have to grasp the scale involved.
It's vast.
When scientists investigate crystalline structures, they're operating across dimensions spanning, what, maybe 30 orders of magnitude?
Easily. It starts quite literally out in space.
Really? How so?
Well, our sources remind us the investigation starts incredibly large. Think about astronomical objects like globular clusters.
Okay, dense star clusters. Astrophysics territory.
Mostly, yes, but the crystalline link comes from minerals found inside meteorites.
Ah, okay.
These tiny crystals offer tangible, solid evidence of chemical processes, crystallization events that happened in the very early universe.
So crystallography has a literal cosmic origin story. That's quite something.
It really is.
But let's come back down to Earth for a second. Here's one of those facts that just makes you stop. Are there really crystals larger than a house?
Oh, absolutely. Yes. The spectacular example is the Cave of the Crystals in Naica, Mexico.
Naica, okay.
These are colossal gypsum crystals, calcium sulfate dihydrate.
Yeah.
They've been measured up to 14 meters long.
14 meters? That's what, about 46 feet?
Exactly. We're talking multi-story, house-sized mineral formations. It's staggering.
How on earth did they get that big? What allowed that?
It comes down to constant physicochemical conditions, just incredibly stable. The cave environment provided this stable geothermal heat source that kept the water saturated with gypsum right at a specific temperature window for an immense period.
How long are we talking?
Estimates suggest this uninterrupted growth persisted for anywhere from, say, 100,000 to maybe even 1,000,000 years.
Wow.
That sustained, slow, perfect environment is really the key to producing such macroscopic wonders.
So patience, basically. Lots and lots of geological patience.
Precisely.
Then we zoom down to the scale we're probably more familiar with, right? The mineralogical objects you see in museums.
Yeah, things ranging from maybe the size of a football down to a ladybird, say 22 centimeters down to 1 centimeter roughly.
We might look at a deep green fluorite crystal, for instance, maybe about 2 centimeters across.
Common size.
But to truly understand its character, its properties, we have to look past the surface,
You have to zoom right in.
down to the microscopic scale of molecules and atoms, the actual building blocks.
And that necessity leads us directly to the formal, precise definition of what a crystal actually is. And this definition is quite rigid.
Okay, let's hear it.
A crystal is defined as a homogeneous, anisotropic solid state whose building blocks are strictly three-dimensional, periodically ordered.
Okay, homogeneous anisotropic. But that last part, three-dimensional periodically ordered, that seems like the absolute core requirement.
It is.
That's what separates, say, a diamond from a piece of glass. If I have a piece of plastic that looks solid, why isn't that a crystal?
Because of that periodic order,
Mhm.
amorphous materials like glass, wood, plastic, they're solid, sure. They might have a fixed external shape,
Right.
but their internal arrangement is essentially random or, at least lacks that infinite repeating symmetrical pattern required.
So no repeating pattern, no crystal.
That periodic order is the absolute distinguishing feature. And interestingly, the word structure itself, which we use so casually, it derives from the Latin structura, meaning fitting together or building. It was primarily an architectural term before it was adopted by natural sciences back in the 17th century to describe the constitution of substances.
Huh. Architecture to atoms. Okay. Let's focus on that other essential characteristic you mentioned, anisotropy.
Yes, anisotropy.
It sounds complex, but if I understand correctly, it just means the physical properties of the material are directional. They depend on which way you measure.
That's exactly it. It means the material has an internal grain, kind of like wood,
Yeah.
but this grain is dictated atom by atom.
Okay.
The physical properties, whether it's how light passes through or electrical conductivity or even mechanical hardness, they will vary depending on the direction along which you measure them.
Can you give us a vivid example? How does that play out practically?
Hardness is probably the easiest one to visualize. Imagine we have a crystal, right, and we try to apply pressure or maybe scratch its surface.
Yeah.
If you test the hardness by applying pressure to the top face, and then you repeat the test on a side face, or maybe cut the crystal diagonally, the resulting indentation or the ease of scratching will be vastly different.
Why, though?
Because the force required to displace those internal building blocks depends entirely on the specific sequence and relative position of those blocks in that particular direction. The internal periodic atomic geometry literally steers how the external force is resisted.
So the atoms line up differently depending on the direction, making it harder or easier to push them around.
Precisely. Hashtag tag 1.2, the correspondence principle in snowflakes.
Yeah.
And this internal steering effect, it's codified in a very old but really crucial idea called the correspondence principle.
Correspondence principle. Okay.
This principle states that the external form, the morphology of the crystal,
Its visible shape.
corresponds directly and absolutely to its internal atomic structure. There's a direct link.
We see this complexity in things like quartz, right? Rock crystals, which are just colorless quartz, text SiO2. They have this highly intricate, often six-sided external shape.
Very characteristic.
It seems almost impossible to visually connect that macroscopic shape back to the simplest building block, the text SiO44 tetrahedron. It's just a little pyramid shape.
But the connection is perfect. It really is.
Yeah.
If you take that simple text SiO4 tetrahedron and you assemble an enormous number of them, following the rules of crystallography.
Stacking them in a specific, repeating way.
Yes. The resulting full atomic model perfectly dictates the complex external shape of the macroscopic crystal. Whether it's standard colorless quartz or purple amethyst or pink rose quartz, the underlying rule is the same.
The ultimate demonstration of this principle, though, the one that makes everyone genuinely curious, has to be the snowflake.
Ah, yes, the classic example.
Why does every single ice crystal or snowflake, regardless of its specific shape, whether it's a thin plate or a column or a highly branched dendrite, why does it always possess hexagonal symmetry? 6 sides, 6 points.
It's all about the molecular geometry of water itself.
Okay.
It's a 3-atomic, angled molecule, and critically, it's highly polar.
Meaning it has charged ends, right?
Exactly. The oxygen atom carries a slight negative partial charge, and the 2 hydrogen atoms carry slight positive partial charges.
And when water cools down and starts to aggregate to form ice,
the hydrogen bonds, that attraction between those positive and negative partial charges, they force the molecules to orient themselves in a very specific way relative to each other.
specific arrangements.
Precisely. And that specific attraction pattern naturally forces the growing solid cluster to develop that visible outer hexagonal shape.
So the 6-fold symmetry is locked in from the start at the molecular level.
It's constant and universal. Now, the form of the snowflake, the way it branches out into dendrites or forms plates,
That varies a lot.
that's merely determined by the external conditions, the precise temperature and humidity during its growth. But the underlying 6-fold symmetry, dictated by the textinomolecule's geometry and bonding, that is non-negotiable.
So even those long, thin ice needles you sometimes see, they looked totally linear, not hexagonal at all.
Right, but if you were able to look straight down their long axis, like looking down a pipe, you would still see the 6-sided cross-section reflecting that inner structure. The internal rule always governs the external reality.
Fascinating. The invisible dictates the visible. Okay, so we've established this crucial link, the correspondence principle, between the internal atomic structure and the external shape we see.
Yes.
Now we need to find the fundamental blueprint for that internal structure, and that blueprint is the unit cell.
The single most important concept in crystallography, arguably. We're looking for the absolute minimum repeating unit.
The smallest possible block that contains all the information.
Exactly. And to find it, we have to follow two very strict rules.
Okay, what are they?
First, we must use only one kind of regular building unit. No mixing shapes.
Got it.
Second, that unit must be able to completely fill all of 3D space purely by translation.
Meaning just sliding it. No rotating or flipping.
Pure sliding. Shift it along the three spatial directions, X, Y, Z, and you must perfectly fill space with no gaps and no overlaps.
That sounds simple, but geometrically it rules out a lot of shapes, doesn't it?
It does. If you try to, say, fill space with regular pentagons or certain kinds of prisms, you quickly realize you either leave gaps or you need to rotate the blocks to make them fit.
Which violates the pure translation rule.
Precisely. That's why the answer is mathematically constrained. The only shape that works is a parallel pipette.
A parallelepiped. Okay, remind me.
Any geometric body confined by 6 faces, where each face is a parallelogram. Think of a tilted box.
Ah, right, like a squashed cube.
It could be. That shape ensures pure translation can fill space. Now, the most symmetric example, and the easiest one to visualize and work with, is indeed the cube.
Makes sense. So the unit cell, whether it's a perfect cube or some tilted parallelepiped, is characterized entirely by its dimensions.
It's metric, yes. That's the 3 edge lengths, usually called A, B, C2, and the 3 angles alpha, beta, gamma between those edges.
6 parameters define the box.
Exactly. And based purely on how those 6 parameters relate to each other, are the sides equal? Are the angles 90 degrees? We can classify every single crystal ever found into just 7 fundamental crystal systems.
Only 7. That's amazing. For all the complexity we see, it boils down to just 7 basic blueprints.
Just 7 underlying geometries. We can define them by looking at the extremes of symmetry.
Okay, let's do that. What's the least symmetric?
At the very bottom, we have the triclinic system. This has the lowest symmetry possible. Here, a baconate gamma. And critically, none of those angles are 90 degrees. It's a completely general, often quite distorted parallel pipette.
The most unrestricted box, you could say.
In a way, yes. Then at the absolute top of the symmetry scale, we find the cubic system, the perfect cube. Here, A, B, C, and all angles, alpha, beta, gamma, are exactly $90 circ. Maximum symmetry.
Okay, so triclinic at the bottom, cubic at the top. What about the ones in between?
The other 5 systems, monoclinic, orthorhombic, tetragonal, hexagonal, and trigonal, they fill the space between these extremes. Each is defined by specific fixed metric requirements.
For instance?
We'll take the monoclinic system. It's one step up from triclinic. We require 2 angles to be 90 degrees, but one angle is allowed to be different. And just by convention, crystallographers always call that unique non-90 degree angle dar beta.
Just a naming standard everyone agrees on.
Exactly. It's crucial here, though, to distinguish between the abstract geometric arrangement and the actual physical content inside the unit cell.
Right. The box versus what's in the box.
Precisely. We call the infinite abstract array of repeating points that defines the translational symmetry the lattice. It's just points in space.
A framework.
Yes. Then the motif, or sometimes called the basis, is the physical content, the actual atom or molecule or group of atoms that sits identically at each and every one of those lattice points.
Okay.
So the complete crystal structure is always the sum, lattice plus motif, and the lattice itself, the framework of points, is always chosen to show the maximum possible symmetry inherent to that particular crystal system.
Got it. Abstract grid plus the actual stuff arranged on the grid. Hashtag 2.2 external morphology and Miller indices. Now here's a puzzle. Even though we only have these 7 basic types of unit cells, the resulting external shapes, the morphology we actually see, is staggeringly diverse. It's not just 7 shapes.
Not at all.
Got it.
Far from it. Take pyrite, for example. Iron sulfide, TextFES22. It's a classic cubic system mineral. Its unit cell is cubic.
Okay.
Yet pyrite is known to form over 60 different distinct external shapes, including the perfect cube, yes, but also the 8-sided octahedron, and the very distinctive, almost football-shaped pentagonal dodecahedron.
60 shapes from a cubic box. How does that happen?
It depends on which internal planes happen to grow outwards to become the boundary faces, and how fast they grow relative to each other. This complexity forces crystallographers to be extremely precise when they describe a crystal shape.
You need specific terminology.
We do. We use 2 specific German terms, actually, that have become standard. First is Tracht, T-R-A-C-H-T. It describes the number and the combination of different types of faces present on the crystal. You can think of it like the costume the crystal wears. Which faces does it choose to show?
Okay, the set of faces present. What's the second term?
The second term is habitus. Habitus. Habitus describes the relative size and development of those faces. This defines the overall shape.
Ah, so tract is which faces, habitus is how big they are relative to each other.
Exactly. For instance, you could have two pyrite crystals that have the same tract, meaning they both show, say, cube faces and octahedron faces.
Right.
But one might have a cubic habitus. It's dominated by large cube faces, looking mostly like a cube. The other might have an octahedral habitus, dominated by large octahedron faces, looking mostly like an octahedron. Same faces present, completely different overall shape.
Okay, that clarifies things. Now, to navigate all this complexity, to talk about specific faces, we need some kind of address system.
We absolutely do.
And that brings us to Miller indices, usually written as low
Yes,
sum.
Miller indices. They are ingenious, really, because they relate the external face directly back to the internal periodicity of the lattice.
How do they work?
They essentially label the infinite stacks of lattice planes inside the crystal. And consequently, they label the external crystal faces that are parallel to those internal planes.
Okay.
They're calculated as the normalized reciprocals of the points where a specific crystal face intersects the unit cell axis, ABC2, relative to some chosen standard face, which is usually designated as 111.
Reciprocals. That sounds a bit mathematical. Can you simplify?
Think of it this way. If a face is labeled 100, that 1 in the first position means it intersects the A axis at 1 unit length. The zeros mean it's parallel to the B, and C axis it never intersects them.
Ah, okay. So 100 is perpendicular to A, 0, perpendicular to B, 0, 1 perpendicular to C. Those are the cube faces in a cubic system.
Exactly, and this brings us back to the correspondence principle again.
The link between internal and external.
Yes. The outermost plane of a given set of parallel lattice planes exactly forms the boundary face of a crystal. So if we know the internal atomic arrangement in the lattice, we can predict the possible external faces and label them with Miller indices.
I've noticed there are different ways to write these indices. Sometimes parentheses like HAL, sometimes curly brackets. What's the difference?
Good question. The parentheses, HHAL, denote a specific individual face. The curly brackets define what's called a face symbol or a form.
A form.
Yes. It groups together all the equivalent faces, that is, all the faces that are mathematically and physically related to each other by the crystal's internal symmetry operations. They have the same absolute values of H, K, and L, just maybe different signs or orders.
So for a cube?
For a cube, the form includes the front face, 100, the back face, that's 1 bar, meaning -1, and the four side faces, 0, 0, 1, and 100 bar. All 6 faces of the cube belong to the form.
It's a way to talk about a whole set of symmetry-related faces at once.
Precisely. It's the standard way to denote a crystallographic form. And this whole system, unit cells, crystal systems, Miller indices, this is the language that modern software like Vesta, which is used for visualization, uses to construct and display these complex structures.
Got it. The address system for the crystal's architecture. Okay, we've got the unit cell, the basic box, and we have Miller indices to label the faces. Now, let's talk pure symmetry. We need to classify the arrangements of these faces.
Right. We start with point symmetry. These are symmetry operations where at least one point, usually the center of the object, remains fixed and unmoved throughout the operation.
Like spinning something on a fixed axis.
Exactly. And for any macroscopic object like a crystal, there are exactly 5 fundamental point symmetry elements we need to consider.
Only 5. Okay, let's list them.
First, the simplest one, the trivial identity, usually symbolized as 1 or sometimes E. It's just rotating the object by 360 degrees. It brings it back to itself, so technically it's a symmetry operation.
Okay, doing nothing counts. What's next?
Second, the mirror plane, symbolized as M, or sometimes the Greek letter sigma. Sigma. It's just a reflection across a plane, like looking in a mirror.
Simple enough. Third.
Third is an axis of rotation, symbolized M, or sometimes centitalers. This involves rotation by an angle of $360 divided by 9. So a two-fold axis means 180-degree rotation, three-fold is 120 degrees, four-fold is 90, six-fold is 60.
Right. Now, the next two get a bit more abstract, I think. The center of inversion.
Yes, the center of inversion, symbolized as 1 bar, or sometimes I. This is a point reflection. Imagine every point on the crystal surface is moved through the central point to an equal distance on the exact opposite side.
So top left becomes bottom right, front center becomes back center.
Exactly. It's called 1 bar, possibly because it relates to mapping a point XYZ to XYZ, like multiplying by -1. This is a slightly quirky notation.
Okay. And the fifth and final point symmetry element.
The roto-inversion axis, symbolized A-coupled E bars, is a coupled operation that combines rotation and inversion.
How does that work?
You rotate the object by 360 tora bar, and then you immediately invert the result through the center point. It's a way to describe symmetry that isn't just a simple spin or a simple flip.
Are there simple equivalents? Like, is a cable axis something familiar?
Yes. A Board or roto-inversion axis is exactly the same as just having a center of inversion. And a Board roto-inversion axis turns out to be mathematically identical to having a mirror plane perpendicular to that axis.
Right.
So these operations are all interconnected.
It's interesting. The sources mention a link between symmetry and beauty here. Like, perfect bilateral symmetry in human faces is often idealized.
Right.
But mathematically speaking, slight deviations from that perfect mirror image are often perceived as subjectively more attractive or interesting.
It's a fascinating aside, isn't it? How our aesthetic sense interacts with these fundamental geometric concepts. But let's get back to the strict rules of the solid state.
Okay.
We absolutely must stress the critical limitation in crystallography regarding rotation axis. In periodic crystals, the order and end of a rotation axis is strictly limited to values of 2, 3, 4, and 6.
No five-fold, no seven-fold or higher. Why not? If I can easily draw a five-pointed star or a regular pentagon, why is that structure forbidden in a natural periodic crystal lattice?
It comes back to that requirement for translation and completely filling space without gaps.
Ah, the tiling problem again.
Exactly. You can certainly have an object with five-fold rotational symmetry. But if you try to take a pentagonal unit cell and use pure translation, just sliding it side by side to tile an entire 2D plane or fill a 3D volume, you will inevitably leave gaps. It just doesn't work geometrically.
Squares tile perfectly, hexagons tile perfectly, triangles tile perfectly, but pentagons don't.
Correct. Only rotational symmetries of 2, 3, 4, and 6 are mathematically compatible with an infinite periodic lattice. For centuries, this rule was considered an absolutely untouchable fundamental law of the solid state. No exceptions. Hashtag tag 3.2, the 32 crystal classes. Okay, so we have these 5-point symmetry elements, but we're restricted to using only 2, 3, 4, and 6-fold rotations or roto-inversions.
Right.
Now, if we consider all the possible ways to combine these allowed symmetry elements around a single point, it turns out there are exactly 32 unique combinations possible.
32, that's it.
That's it. These 32 distinct symmetry combinations are known as the 32 crystal classes, or sometimes the 32 crystallographic point groups.
So these 32 classes represent the definitive list of all possible ways the faces of a crystal can be arranged symmetrically around its center point.
Correct. And they are systematically assigned across the 7 crystal systems we discussed earlier, based on the minimum symmetry required by each system.
Let's look at the extremes again. What about the lowest symmetry system, triclinic?
The triclinic system, having the least symmetry constraints, alpha Ni, beta Ni, gamma, is home to the 2 absolute lowest symmetry crystal classes.
Which are?
Class 1, which has no symmetry whatsoever other than the trivial identity operation, and Class Bar, which has only a center of inversion and nothing else.
Very simple. Any common minerals in these classes?
Oh yes, very common ones actually. Things like the feldspars, which make up a huge portion of the Earth's crust, and minerals like turquoise belong here. Their low symmetry makes their structures complex to analyze, but they are incredibly abundant.
Okay, moving up a step in symmetry to the monoclinic system, what classes do we find there?
The monoclinic system requires at least one 2-fold axis or one mirror plane. This allows for 3 possible crystal classes. Class 2, just a single 2-fold axis. Class A, just a single mirror plane. And Class 2 mil is 2. Over with.
Can you elaborate on 2 mil today? That notation seems common.
It is very common. Class 2 Mellers is known as the monoclinic prismatic class. The notation means you have a 2-fold axis of rotation, and you also have a mirror plane that is oriented perpendicular to that axis, indicated by the slash.
Great.
Now, critically, when you have both a 2-fold axis and a perpendicular mirror plane present, these 2 elements combined automatically generate a center of inversion, right where they intersect.
Ah, so the inversion center is implied.
Exactly.
Yeah.
It's a consequence of the other 2 symmetries, so we don't need to explicitly include metocadal in the standard 2-Meller notation. Symmetry elements combine in very predictable ways like this.
Any examples of 2 melanin minerals?
Very common ones again. Gypsum, the mineral in drywall, and the beautiful blue mineral azurite are classic examples exhibiting 2-Meller symmetry.
What about the orthorhombic system? The notation seems different there, often with 3 symbols like MLM tuna poo.
That's right. For orthorhombic, tetragonal, hexagonal, and cubic systems, the symmetry notation usually refers to specific directions in the crystal. Orthorhombic has three mutually perpendicular axes of potentially different lengths, but all angles are 90 degrees. So we need to specify the symmetry along each of these three principal directions.
So Munifier means?
And Munifiers is the rhombic pyramidal class. It means if you look down the first principal direction, say the ask axis, you see a mirror plane. Look down the second direction, you see another mirror plane. But look down the third direction, you only see a twofold axis of rotation too.
So it's not symmetric in all directions.
Not equally, no. An excellent mineral example here is hemimorphite. Its name literally means semi-surface because the crystal exhibits polarity. It looks different on opposite ends along this axis. One end might be sharply terminated, the other end might be rounded or have different faces. This happens because the Sandor direction only has that twofold rotation, not mirror planes like the 800 directions. That lack of mirror symmetry along Sandor makes the two ends fundamentally different.
Fascinating how the notation directly tells you about the potential physical appearance. Let's tackle a high symmetry example. The sources mention the hexagonal wine barrel.
Ah, yes, a good visualization for the highest symmetry class in the hexagonal system. 6 millimolars. It's called the diagonal to pyramidal class.
Okay, 6 millimolars. Break that down for us. It looks intimidating.
It does, but it's actually very descriptive once you know the code. The notation is broken down by directions. The first part, 6 molars of calors, tells us about the symmetry along the principal unique axis in the hexagonal system, which is the Sandel axis.
So along SAM, there's a six-fold rotation axis, 6, and a mirror plane perpendicular to it.
Exactly. Like the top and bottom faces of the barrel are related by rotation, and there's a mirror plane slicing horizontally through the middle.
Got it. What about the next two M's?
They describe the symmetry elements along the secondary directions, perpendicular to C. The second symbol, the middle M, usually denotes symmetry perpendicular to the crystallographic A-axes. There are three equivalent A-axes in the hexagonal system. So there's a set of vertical mirror planes passing through the axes.
Okay.
The third symbol, the last M, denotes symmetry perpendicular to directions between the axes, essentially along the face diagonals. So there's another set of vertical mirror planes cutting between the first set.
So you have the six-fold axis, the horizontal mirror, and two different sets of vertical mirror planes all intersecting.
Precisely. And again, this very high level of symmetry generates other elements automatically. In the 6-element law class, these specified elements automatically generate three additional twofold axes of rotation lying in the horizontal mirror plane.
Wow, that's a lot of symmetry packed in. Any minerals like this?
Minerals like beryl, which includes emerald and aquamarine, and covalite, a copper sulfide, crystallize in this high symmetry 6 millimole class. Understanding these 32 classes is really the foundation for analyzing external crystal forms. Often, experienced mineralogists can identify a substance, or at least narrow it down significantly, just by examining its external shape and identifying its point group symmetry elements alone.
The shape tells the story, if you know how to read the symmetry.
That's the essence of it.
Yeah.
Okay, we've covered point symmetry, which describes the symmetry of finite objects around a fixed point. Now we need to make the leap to space symmetry.
Which deals with infinite repeating patterns.
Exactly. Plane symmetry deals with isolated objects. Space symmetry, or the symmetry of periodic patterns, requires us to add translation, that sliding motion, as a fundamental symmetry operation.
Okay. Before we dive into the complexities of 3D space groups, the source material takes an interesting detour into 2D symmetry. You mentioned the 17 plane groups or wallpaper groups earlier.
Yes. It's a really useful stepping stone. These 17 groups describe all possible ways to arrange a pattern periodically in a 2D plane. Think of tiled floors, actual wallpaper patterns, Escher's drawings, ancient Islamic mosaics. They all must conform to one of these 17 symmetry types.
And this has practical applications beyond art and design.
Oh, absolutely. These patterns are built upon the 5 fundamental Bravais lattices of the plane: oblique, rectangular, centered, rectangular, square, and hexagonal grids. But to get all 17 patterns, we need to introduce the 2D version of a translation-coupled symmetry operation, the glide reflection line.
A glide reflection. That's like mirroring something and then sliding it parallel to the mirror line.
Precisely. Like leaving footprints in the sand, each print is a reflection of the other foot shifted forward. You need this operation in addition to the simple rotation and reflection to describe all 17 possible 2D periodic patterns.
Why are these 17 plane groups so important in science, though?
They are absolutely crucial in surface physics and heterogeneous catalysis. Think about it. Any flat surface or face bounding a 3D crystal can itself be described as a 2D periodic pattern, governed by one of the 5 planar Bravais lattices, and potentially one of the 17 plane groups.
So if you're a chemist trying to make a reaction happen on the surface of, say, an iron catalyst,
Like in the Haber-Bosch process for making ammonia, a classic example.
right, that reaction happens on the 2D surface of the iron particles.
Exactly. And researchers discovered decades ago that the specific crystallographic face of the iron catalyst exposed to the reactants matters immensely. Certain faces, like the ones indexed as 111 and 211 in the cubic iron structure, are highly reactive for ammonia synthesis. Other faces are nearly inert.
Why the difference?
Because the precise geometric arrangement of the iron atoms on those specific 2D surfaces, an arrangement dictated by the rules of 2D symmetry, one of the 17 plane groups presents the incoming nitrogen and hydrogen molecules with a highly efficient configuration of active sites for breaking bonds and forming ammonia. A slight change in the 2D surface symmetry leads to a massive change in chemical efficiency.
So understanding 2D wallpaper patterns is key to designing better catalysts.
It's fundamental to understanding surface reactivity, yes. Hashtag tag tag 4.1 3D translational elements. Okay, now let's extend this into 3 dimensions. To describe the symmetry of 3D periodic crystals, we need to incorporate 2 new types of symmetry operations that intrinsically involve translation.
Extending the 2D ideas. What's the first one?
The first is the glide plane. This is the direct 3D analog of the 2D glide reflection line.
So it involves mirroring across a plane, plus a simultaneous translation parallel to that plane.
Correct. We have simple glide planes, often symbolized by A, B, or A or 2R, where the translation component is exactly half a unit cell length along one of the crystallographic axes parallel to the plane.
Straightforward enough.
But we also have more complicated types. There are diagonal glide planes, usually symbolized N, where the translation is half a unit cell length along a face diagonal, t.g. half along A plus half along B. And even trickier ones like D glide planes, sometimes called diamond glides, which involve translations of a quarter unit cell length. They add significant complexity to the internal symmetry.
Okay, glide planes are mirror plus slide. What's the second translational element?
The second one is the screw axis. This one is often more visually intuitive.
How so?
A screw axis combines rotation with a simultaneous translation along the axis of rotation. It generates helical symmetry.
Ah, like walking up a spiral staircase, or the structure of a DNA double helix.
Exactly like those. You rotate and move upwards or downwards at the same time. Just like pure rotation axes in crystals, screw axes are limited by the crystallographic restriction theorem. Their rotational component can only be 1, 2, 3, 4, or 6.
So you can have a 2-fold screw axis, a 3-fold, 4-fold, 6-fold. Can you give an example? Say the difference between a 301/21 and a 301/2 screw axis. They sound similar.
They're closely related. A 3-fold rotation means spinning by a $120 circ. A 301/1 screw axis 3-1 combines that $120 circ rotation with a translation of exactly $13 the unit cell length parallel to the axis.
Okay.
A $3.2 screw axis 322 also involves a 122 rotation, but the translation component is $203 the unit cell length along the axis.
So different amounts of rise for the same term.
Precisely. If you trace the path of a point being operated on by these axes, you'll generate helices. And critically, the 301 helix and the 322 helix are mirror images of each other. One is right-handed, the other is left-handed.
Like the threads on a screw.
Exactly. They form what's called an enantiomorphic pair. This concept of handedness, or chirality, generated by screw axes, is incredibly important when dealing with the structures of chiral molecules, like proteins or pharmaceuticals.
Okay, so we have the 14 possible 3D lattice types, the Bravais lattices, the 32 point groups, crystal classes, and now these 2 new translational symmetry elements, glide planes and screw axes. What happens when you combine all of these possibilities?
When you systematically combine the 14 Bravais lattices with the 32 allowed crystallographic point groups, and you consider all the possible ways to incorporate glide planes and screw axes consistent with those point groups and lattices, you arrive at the ultimate classification system for periodic structures, the space groups.
The final blueprint list, how many are there?
After all the mathematical derivation done independently by Fedorov, Schoenflies, and Berlow in the late 19th century, it turns out there are exactly 230 unique space groups.
230. That's the absolute limit.
That is the theoretical limit. These 230 space groups represent every possible way that matter can arrange itself in a 3-dimensionally periodic pattern while obeying the laws of symmetry. It's a complete and exhaustive description.
The notation for space groups must be complex then, encoding all that information. Let's try to break down an example from the source. A text Pika 21011. It's from the orthorhombic system.
Okay, text Pika 21011. Let's decode it piece by piece.
The first letter, P, what's that?
P indicates the Bravais lattice type. In this case, P stands for primitive. That means the unit cell has lattice points only at its corners, nowhere else, like in the center or on the faces.
Okay, primitive lattice, then CA21. These refer to symmetry elements along specific directions.
Yes, in the orthorhombic system, the next three symbols refer to the symmetry elements associated with the 10 and 10R axes, respectively. So the C in the first position means there's a C-glide plane perpendicular to the z-axis.
Meaning mirror across that plane, then slide half a unit cell along C.
Correct. The A in the second position means there's an A-glide plane perpendicular to the bag axis, mirror, then slide half along A.
Got it. And the 21 in the third position.
That indicates a 2-1 screw axis parallel to the third direction, the C-axis. So rotate 180 degrees around C, then translate half a unit cell along C.
Wow. So every single symbol in that compact notation tells a crystallographer precisely what symmetry operations exist and where they are located inside the unit cell.
That's the power of the Hermann-Mauguin notation system used for space groups. It's incredibly information dense.
Let's look at a really concrete, familiar example. Rock salt, common table salt, textine keel. What's its structure like in this system?
Rock salt crystallizes in the cubic system, which has high symmetry. Its specific space group is Fambar 3L.
Okay, break that down to F.
F stands for face-centered cubic Bravais lattice. It means there are lattice points at the corners and in the center of each of the 6 faces of the cubic unit cell.
Okay, and Mabar 3.
That part, Mumbar-Mural, or sometimes Rittendemer-Mural, represents the point group symmetry associated with the lattice points. It's one of the highest possible point symmetries in the cubic system, involving multiple mirror planes and rotoinversion acts. It's very symmetric.
Visually, the structure looks pretty simple, right? Just alternating sodium plus ions in a perfect, tidy grid.
It does look simple, yes. Each sodium ion is surrounded by 6 chlorine ions in an octahedron, and vice versa, each chlorine is surrounded by 6 sodiums.
But you mentioned earlier that high symmetry can hide complexity. Is that happening here?
This is where we uncover a really crucial concept. Crystallographers use what the source calls the miracle of simplicity, achieved through special positions.
Okay.
If you look up the full description of the Fulbar-Muriel space group in the standard reference books, the international tables for crystallography, the overall complexity described is enormous. The most general position within that unit cell, a point that doesn't sit on any symmetry element, has a multiplicity of 192.
Meaning one atom placed there would generate 191 other equivalent atoms within the unit cell through symmetry operations.
Exactly, which seems totally counterintuitive for a simple compound like NaCl, where we know there are only 4 Ni and 4 Cl per unit cell in the F-centered lattice.
So how does that work? Why isn't it incredibly complex?
It's because the sodium and chloride ions do not occupy those general positions. They occupy very specific, highly symmetrical locations within the unit cell known as Wyckoff positions.
Wyckoff positions.
Yes, these are specific coordinates within the unit cell that happen to lie on one or more symmetry elements, like on a mirror plane or on a rotation axis or at the center of inversion.
Ah, so the atoms are sitting right on the symmetry operators.
Precisely. In NaCl, the Na plus ions occupy the Wyckoff position labeled $4, and the Cl ions occupy the position $4. These positions have very high site symmetry. They coincide with multiple symmetry elements.
And what does that do?
When an atom sits on a high symmetry Wyckoff site, many of the space group symmetry operations leave that atom's position unchanged or map it onto itself. This drastically reduces the number of equivalent positions generated at its multiplicity. For the 4 Grad and 4 Bright sites in 4 Billier, the multiplicity is only 4, not 192.
So understanding which specific Wyckoff position the atoms occupy is the shortcut that makes sense of the whole structure and explains its apparent simplicity.
Absolutely. It simplifies the description enormously. And that simple, tidy, highly symmetric structure directly explains NaCl's physical properties. For example, rock salt is quite brittle and shows perfect cleavage. It breaks cleanly along the 3 equivalent cube faces, the planes.
Why does it break so easily along those specific planes?
Think about the structure. Along the planes, you have layers of alternating Na plus and Cl ions. If you apply a small shear force, you only need to shift one layer relative to the next by about half an ion diameter.
What happens then?
Suddenly, you bring Na plus ions directly over Na plus ions and Cl ions direct over Cl ions across that slip plane. You get massive electrostatic repulsion between these like-charged ions. Pop! The crystal cleaves cleanly right along that plane. The structure dictates the fracture behavior.
Amazing. And for centuries, this whole system, defined by the 14 lattices, 32-point groups, and culminating in these 230 space groups, was considered the complete and final architectural manual for all crystalline matter. The rules were set.
That was the dogma, yes. Complete, perfect, and allowing no exceptions, especially regarding that forbidden five-fold symmetry.
So that perfect, mathematically elegant universe of 230 space groups, where five-fold symmetry was strictly impossible because it couldn't tile space periodically, that was treated as absolute law.
It was fundamental solid-state physics and chemistry.
Which makes the next chapter in our story, the discovery of this forbidden symmetry, one of the really great scientific dramas of the 20th century.
It really was a paradigm shift. The rules seemed inviolable because, as we established, you simply cannot tile a 3D volume or even a 2D plane with perfect pentagonal symmetry without leaving gaps. Therefore, perfect periodicity and five-fold rotation were considered mutually exclusive concepts. End of story.
Until 1982, when this scientific paradigm was basically shattered by a materials scientist named Dan Shechtman.
That's right. He was using electron diffraction, a technique that probes the internal structure of materials to examine rapidly cooled alloys of aluminum and manganese.
And what did he see?
He saw diffraction patterns, the pattern of spots produced when electrons scatter off the atoms that showed unmistakable sharp spots arranged in perfect five-fold rotational symmetry. And not just five-fold, but also related ten-fold symmetries.
Which should have been impossible according to the 230 space group.
Absolutely impossible. Since the symmetry of the diffraction pattern must perfectly reflect the internal symmetry of the crystal lattice producing it, this observation directly contradicted the fundamental laws of crystallography.
What was the reaction from the scientific community?
Explosive skepticism, bordering on ridicule in some cases. The immediate assumption from many established figures was that Shechtman must have made a mistake.
Like maybe he wasn't looking at a single crystal.
Exactly. The most common explanation offered was twinning, a phenomenon where two or more normal crystals grow together in a specific oriented way that can sometimes mimic higher symmetry in a diffraction pattern, even though the individual crystals are perfectly normal and periodic.
But Shechtman was sure it wasn't twinning.
He was convinced. But the resistance was fierce. This wasn't just a minor debate. It involved real intellectual heavyweights challenging his findings.
The source mentions the famous chemist and double Nobel laureate Linus Pauling was particularly critical.
Yes, Pauling was perhaps the most prominent and vocal denier of Shechtman's findings. He argued forcefully that the results must be due to twinning, and he famously dismissed Shechtman's research by saying something like, "There are no quasi-crystals, only quasi-scientists."
Ouch. That's harsh.
It was. The prevailing view was either twinning or just outright experimental error. But Shechtman was persistent. He gathered more evidence, and crucially, other groups began to reproduce his results in different alloy systems. He was ultimately proven correct.
And these new materials were given a name.
Yes, they were eventually labeled quasi-crystals, short for quasi-periodic crystals.
How do they fundamentally break the old definition of a crystal?
They break the requirement of strict periodicity. Quasi-crystals possess perfect, long-range orientational symmetry. The atoms maintain specific relative orientations over long distances, which is why they produce sharp diffraction patterns like traditional crystals. But they have no translational symmetry. The pattern never repeats itself exactly. They are fundamentally periodic.
So ordered, but not repeating, like the Penrose tiles we'll discuss.
Exactly like that concept. And this discovery was so profound, so fundamental, that it forced the ultimate gatekeepers of the field, the International Union of Crystallography, the IUCR, to actually change the official foundational definition of what a crystal is.
They had to rewrite the textbook definition.
They did. They had to step away from the definition, relying solely on a periodic atomic arrangement, the lattice. The new definition, adopted in the 1990s, is based purely on the observable experimental outcome. A crystal is now essentially defined as any solid form of matter that yields a diffraction pattern with essentially discrete, sharp peaks, defined Bragg peaks.
So if it diffracts like a crystal, it is a crystal, whether it's periodic or not.
That's the modern understanding. It encompasses both traditional periodic crystals and these newer aperiodic quasicrystals under the same umbrella. Shechtman, by the way, was eventually awarded the Nobel Prize in Chemistry in 2011 for this discovery.
A vindication after all that initial skepticism. Hashtag 5.1, the math behind the anomaly. So if quasicrystals aren't periodic, how did mathematicians and physicists make sense of their structure? The math behind this aperiodic order must have existed somewhere, right?
It did, yes. Theoretical groundwork that perfectly described this kind of non-periodic order had actually been laid years earlier, primarily in the 1970s, by the mathematical physicist Roger Penrose.
Penrose, famous for his work on general relativity and black holes.
The very same. He was also deeply interested in tiling problems, and he discovered what are now known as Penrose tilings.
What are they?
Penrose showed mathematically that you could completely cover a 2D plane without any gaps using sets of tiles with shapes based on five-fold symmetry specifically. Just two different kinds of rhombi, often called a thick rhombus and a thin rhombus.
And the pattern they make isn't repetitive.
No, the resulting tiling is inherently non-periodic. The pattern never repeats itself exactly, no matter how far you extend it. However, it still possesses perfect local five-fold rotational symmetry. Patches of the tiling look five-fold symmetric.
So Penrose had found a mathematical way to create ordered but non-repeating patterns with forbidden symmetry, years before they were found in actual materials.
Exactly. It was the theoretical proof that long-range aperiodic order compatible with five-fold symmetry was mathematically viable. Shechtman's discovery provided the physical realization.
Okay, if quasicrystals defy the normal 3D lattice rules and the 230 space groups, how do crystallographers actually describe their complex atomic structures today?
They have to use a more abstract mathematical framework. They employ the concept of higher dimensional crystallography.
Higher dimensions, like 4D or 5D space.
Even higher, typically 5D or 6D space. The idea is that while the quasicrystal structure is aperiodic in the three physical dimensions we inhabit,
Right.
it can be mathematically described as being perfectly periodic if you embed it within a higher dimensional space, like a six-dimensional hyperspace.
Wow. Okay, how does that work?
You imagine a perfectly normal periodic lattice existing in 6D. Then you slice through this 6D lattice with our familiar 3D space at a specific irrational angle. The points where the 6D lattice intersects our 3D slice define the atomic positions of the quasicrystal.
And because the slice is at an irrational angle relative to the 6D lattice,
The resulting pattern of points in our 3D space is ordered. It comes from a periodic 6D structure, but non-repeating. It never hits the 6D lattice points in the same way again. It generates the aperiodic structure.
that's quite a mental leap. Is there a specific mathematical key to this projection from 6D down to 3D?
Yes, there is. The projection angle, or more precisely, the mathematical relationship used in this cut and project method from 6D space down to 3D space, fundamentally involves the golden ratio.
The golden ratio, approximately 1.618. That number pops up everywhere.
It really does, for an approx 1.618034. It's an irrational number deeply connected to pentagonal symmetry and icosahedral symmetry. It features heavily in the mathematics of projecting the 6D periodic lattice down to the 3D aperiodic quasicrystal structure.
And is this golden ratio just theoretical, or does it show up physically in the quasicrystals themselves?
Oh, it shows up physically, absolutely.
Yeah.
For one thing, the ratio of the edge lengths of the two rhombies used in the 2D Penrose tiling is exactly figural. More strikingly, when you manage to grow single crystals of quasicrystalline alloys large enough to see their external shape.
Their morphology.
Yes, they often grow into highly geometric shapes that exhibit the forbidden five-fold symmetry externally. Common shapes are the icosahedron, a solid with 20 identical equilateral triangular faces, or the regular pentagonal dodecahedron, a solid with 12 identical regular pentagonal faces.
Both shapes intimately related to five-fold symmetry.
Exactly. And if you measure the ratio of the edge lengths to various diagonal lengths within these polyhedral quasicrystal shapes, you find that those ratios correspond exactly to the golden ratio. Yeah.
So the forbidden geometry manifests itself both internally in the diffraction pattern and externally in the crystal shape, mathematically linked by the golden ratio.
It's a beautiful convergence of higher dimensional mathematics, aperiodic order, and tangible physical reality. A true revolution in our understanding of ordered matter.
Okay. Having explored the fundamental rules of symmetry, both periodic and aperiodic, let's see how these principles directly govern the function of some really important advanced materials. Let's start with ferroelectrics.
Right, ferroelectrics. These are often described as smart insulators.
Why smart? What makes them special compared to a normal insulator or dielectric?
Okay, so all dielectric materials, insulators, will polarize slightly. When you put them in an electric field, the positive and negative charges inside shift slightly in response to the field.
Right.
Ferroelectrics are unique because, first, they can exhibit a spontaneous electric polarization, even without an external field. Second, they retain a remnant polarization after an external field is applied and then removed. And third, the direction of that internal polarization can be switched or inverted by applying an opposite electric field.
So they have a built-in switchable electrical polarity.
Exactly. This switchable polarization leads to a characteristic hysteresis loop when you plot polarization versus applied electric field. This behavior is absolutely critical for applications like non-volatile computer memory, ferrum, and in high-performance capacitors.
What's the classic example of a ferroelectric material?
The prototypical example, the one everyone studies first, is barium titanate, TeX-BaTiO3.
Okay, barium titanate. How is its electrical behavior tied to its crystal structure and symmetry?
It's a perfect example of a structure-property relationship driven by symmetry breaking. Above a critical temperature, about 120 Curie, its Curie temperature, TeX-BaTiO3 exists in a highly symmetric cubic crystal structure, known as the perovskite structure.
Cubic, so high symmetry.
Very high symmetry. In this cubic phase, the average position of all the positive charges, from BaO3 plus and T3 plus points line dollars, coincides exactly with the average position of all the negative charges, from the OO2 dollars, right at the center of the unit cell.
So the positive and negative charge centers overlap perfectly.
Yes. Which means there's no net separation of charge, no overall electric dipole moment. The crystal is nonpolar in this high-temperature cubic phase.
But what happens when you cool it down below that critical temperature, below 120 Certex?
As it cools, the ions jostle around less, and the central titanium ion, Ti4+, which is relatively small and highly charged, finds it energetically favorable to displace slightly off-center within the cage of surrounding oxygen ions, the oxygen octahedron.
It shifts just a little bit.
Just a tiny shift, maybe a few hundredths of an angstrom. But that minute atomic displacement causes a massive change. It breaks the cubic symmetry.
How does it break the symmetry?
The shift is typically along one of the original cube axes. This elongation destroys some of the symmetry elements of the cube, particularly the threefold rotation axes that pass through the cube corners. The structure transforms, usually into a slightly elongated tetragonal phase, or other lower symmetry phases like orthorhombic or rhombohedral at even lower temperatures.
And this resulting lower symmetry structure is what allows the ferroelectric property.
Yes. Because the Ti4 plus ion dollars, positive, has shifted relative to the center of the oxygen cage, negative, there is now a net separation of positive and negative charge within the unit cell. This creates a permanent electric dipole moment.
So each unit cell becomes a tiny electric dipole.
Exactly. And because of the crystal structure, these dipoles tend to align with each other in regions called domains, creating a macroscopic polarization. Crucially, the resulting lower symmetry structure possesses what's called a polar axis.
A polar axis.
A direction in the crystal that is not related to its opposite direction by any symmetry operation. For example, in the tetragonal phase of TeX-BaTiO3, the main fourfold rotation axis, the direction that Ti ions shifted along, lacks a mirror plane perpendicular to it, and it lacks a twofold axis perpendicular to it. This asymmetry makes it a polar axis.
And having a polar axis is the key.
It is the necessary structural requirement imposed by symmetry for a material to be able to exhibit not only ferroelectricity, spontaneous switchable polarization, but also related phenomena like piezoelectricity.
Piezoelectricity generating voltage when you press or squeeze it.
Yes, from the Greek piezein, meaning to press, and also pyroelectricity,
Which is?
generating voltage when you change its temperature, from pyre, Greek for fire heat. All three phenomena require the crystal structure to lack certain symmetry elements, specifically a center of inversion, and to possess at least one polar axis. The function is a direct manifestation of the specific symmetry, or lack thereof, of the crystal structure.
Structure dictates function through symmetry.
Now let's shift focus from dense materials like ferroelectrics to a fascinating class of crystals that intentionally defies the traditional idea of dense packing.
You mean materials that are mostly empty space?
Exactly. Most simple crystals, like metals, pack atoms very efficiently. Typically around 74% of the volume is filled in common structures like cubic close packing in HCP or hexagonal close packing HCP. Porous crystals, however, are designed to be non-dense. They act like highly sophisticated molecular scale sieves and sponges.
What are the main types? The source mentions zeolites first.
Yes, zeolites are the classic example. These are naturally occurring, though now often synthesized, framework silicate minerals. They were actually discovered way back in 1756 by a Swedish mineralogist.
What are they made of?
Their framework is built primarily from corner-sharing texturico and text AO of 4,3 tetrahedra. similar to quartz, but linked together in ways that create an open structure containing precisely defined channels and cavities pores running through the material.
And these pores are usually filled with something.
In their natural state, often filled with water molecules and loosely bound positive ions that balance the negative charge introduced by substituting AO force for psi sweaty-butyl. The name zeolite actually comes from Greek words meaning boiling stone, because when heated, the trapped water boils off.
What are they used for? Why is a porous structure useful?
That precise pore structure is why zeolites are indispensable in industry. They are used extensively as catalysts, particularly in petroleum refining for cracking large hydrocarbon molecules into smaller, more useful ones like gasoline.
How does the porosity help catalysis?
The pores act as shape-selective reaction chambers. Only molecules of a certain size and shape can fit into the pores and reach the active catalytic sites within the zeolite framework. This allows chemists to control reactions with incredible precision. They're also widely used for ion exchange, like in water softeners, swapping hard calcium ions for soft sodium ions and for gas separation, filtering molecules based on size.
Okay, so zeolites are nature's molecular sieves, but the source mentions a much newer class of porous materials that takes this concept even further: metal organic frameworks, or MOFs.
Yes, MOFs are a really exciting area of materials chemistry that has exploded since the late 1990s. They represent a different design strategy for creating porosity.
How are they built?
Instead of an inorganic framework like zeolites, MOFs link inorganic building blocks, often small metal oxide clusters called secondary building units, SBUs,
Okay.
using specific organic linker molecules. Think of it like using metal hubs, the SBUs, connected by organic struts, the linkers, to build up a 3D framework, like a molecular construction set.
And the genius is you can choose different hubs and struts to design the final structure.
Precisely. The power of MOF chemistry lies in this reticular synthesis, the ability to rationally design and synthesize frameworks with tailored pore sizes, shapes, and chemical functionalities by choosing the right inorganic SBU and organic linker.
And they can achieve extreme levels of porosity.
That's their defining characteristic. MOFs can be designed to have incredibly high void volumes, sometimes reaching up to 70% or even more of the crystal being empty space.
That must translate into a truly mind-boggling internal surface area.
It does. Because the internal structure is so vast and accessible through the pores, the internal surface area within the material can be enormous. The sources state that 1 single gram of certain MOF materials, about the amount you could fit in a thimble, can exhibit an internal specific surface area of up to 7,000 square meters.
7,000 square meters, that's roughly the size of a professional soccer field.
Exactly. All folded up inside 1 gram of powder. This incredible surface area makes MOFs exceptionally promising candidates for applications like gas storage and separation.
Gas storage? How?
The huge internal surface provides countless sites for gas molecules like hydrogen or methane, natural gas, to absorb onto. This allows much denser storage of gases at lower pressures than in an empty tank. There's a lot of research into using MOFs for onboard natural gas storage for trucks or vehicles, for example.
Now, with zeolites and especially these complex MOFs, how do crystallographers systematically classify these extremely diverse open network structures? It sounds like using the traditional 7 crystal systems or 230 space groups might be unwieldy or not capture the essence of the network itself.
It's a very good point. While MOS still crystallize within the standard framework, they have a unit cell, a space group, describing and comparing their topology, how the building blocks are connected. The overall network structure requires a more abstract approach.
What approach is that?
We use the concepts of network topology. We essentially abstract the structure away from the specific chemical details. We view the framework simply as mathematical networks or graphs, consisting of vertices, nodes, and edges, links.
So the metal cluster SBU becomes a node, and the organic linker becomes an edge connecting nodes.
Exactly. You simplify the complex chemical reality down to its essential connectivity pattern. This allows you to describe the topology of the network itself, regardless of the specific atoms involved.
And this abstraction allows for systematic classification. How?
Yes. By analyzing the geometry and connectivity of these abstract networks, researchers can classify and categorize different MOF structures based on their underlying topology. There are databases like the RCSR, Reticular Chemistry Structure Resource, that assign specific symbols, often 3-letter codes, to known network topologies.
So you can say this MOF has the CLQ topology, primitive cubic, or this one has the diatopology, OQ2, and
Precisely. This topological approach allows scientists to systematically compare, predict, and design new MOF structures based on their desired network connectivity, applying the underlying rules of symmetry and geometry to these abstract points and linkers. It greatly speeds up the discovery process for new porous materials with specific properties.
From atomic symmetry to network topology, the principles extend. Hashtag tag outro. Well, this has certainly been a true deep dive. We started with the absolute foundations, the architectural laws of the crystalline state defining what a crystal is, the 7-unit cell systems, the 32 external symmetry classes, and that seemingly absolute theoretical limit of 230 space groups for periodic arrangements.
Right, the complete blueprint for ordered matter, as it was understood for over a century.
Then we explored the technological implications, seeing how symmetry dictates properties in things like ferroelectrics, before witnessing that entire elegant universe get profoundly shaken up by the discovery of a periodic order in quasicrystals, the forbidden symmetry made real.
A real testament to how science progresses challenging established dogma with careful observation.
And even with all these rules now seemingly updated and defined, the field remains intriguingly unpredictable in some ways. You touched on the phenomenon of polymorphism earlier.
Yes, polymorphism, where a single chemical substance can crystallize into multiple distinct crystal structures, different space groups, different packings, depending on the external conditions like temperature and pressure. Benzene, a simple organic molecule, is a good example. It's known to form at least 5 different crystal structures, polymorphs, under varying pressure.
That inherent variability must make predicting crystal structures incredibly difficult.
It absolutely does. This relates directly to one of the grand challenges in modern material science, crystal structure prediction, CSP. Even if you know the chemical composition and you know all the rules of symmetry and bonding, predicting ab initio, from first principles, exactly which crystal structure a given substance will actually adopt under specific conditions remains incredibly challenging.
Why is it so hard?
Because often, several different possible structures might have very similar energies, making it difficult to know which one will form preferentially or which one is the most stable. It often involves subtle balances of forces. Even with the aid of high-powered supercomputers running sophisticated simulations, CSP results today can still sometimes be, as the source material suggests, almost as unpredictable as trying to forecast the weather long-term. Nature still holds surprises.
Okay, so as a final provocative thought for everyone listening, let's loop back to that idea of anisotropy and material properties, but with a twist.
Right.
We learned about the Mohs hardness scale, that familiar 1 to 10 scale for minerals. Diamond is 10, corundum, like ruby and sapphire, is 9, topaz is 8, quartz is 7, and so on. It measures relative scratch resistance. Diamond scratches corundum, corundum scratches topaz.
A very useful field scale for mineralogists, developed back in 1812.
But it's purely relative. What happens when you measure the absolute hardness? The source mentions the Vickers hardness test, which involves forcing a standardized diamond pyramid into the material under a specific load and measuring the size of the indentation.
Yes, Vickers hardness gives a quantitative measure of resistance to indentation, usually in units of pressure, like gigapascals.
And the numbers are quite different from the Mohs scale suggest, aren't they? Diamond Mohs 10 has a Vickers hardness around 10,000, or even higher depending on the type. Corundum Mohs 9 has a Vickers hardness around 2,000.
That's right. So while corundum is number 9 on the relative scale, diamond number 10 isn't just slightly harder. It's roughly 5 times harder in absolute terms based on indentation resistance.
That's a huge jump between 9 and 10, much bigger than the jump between, say, 8 and 9.
Exactly. That dramatic disparity shows us that even a seemingly simple, intuitive material property like hardness is actually a highly complex, nonlinear manifestation of the deep crystal structure, the bonding strength, the symmetry, and the defect structure within the material. The Mohs scale captures relative ranking, but hides the true magnitude of the differences.
So the big question to mull over then is this. How many other simple-sounding material properties, things we encounter or rely on every day, like tensile strength, electrical conductivity, thermal expansion, optical transparency, are potentially hiding equally dramatic, non-linear complexities and sensitivities deep within the hidden atomic architecture dictated by crystal symmetry?
That's a great question. It reminds us that even in the most common materials around us, there are layers of structural complexity and subtle rules governing their behavior, secrets still waiting to be fully understood and perhaps even exploited. The crystalline world still has much to reveal.